2. Okay, so here is what we know. All right, so now we know that in this region 2, my potential energy is constant. So we just have a constant potential energy there. Okay, and we're going to consider cases in which V is greater than E, which that's depicted on this graph right here. So we're seeing that the potential energy is greater than the kinetic energy that the particle possesses. Okay, and of course, in region 1, that kinetic energy is the total energy because that's all the energy that it has is kinetic. Okay, so we're saying the potential energy is greater than the particle's kinetic energy. And so now setting up this equation, we know this is how we would set up the Schrödinger equation. And now I just want to do the same thing. I want to try to get to that reduced form. Okay, so I can do that by writing second derivative of psi of x. Okay, and then now what I'm going to do here is a couple steps at once here. I'm going to subtract the v psi over, okay, and collecting like terms, that's going to give me e minus v times psi of x, right? I subtract v psi over and then collect terms. And then also remember I have those constants that I want to push over to the other side. So that's going to be negative 2m over h bar squared, okay? And now what I can do is add that back over to the other side to get this into the reduced form. And so, you know, there's a couple different ways you could have done that algebraically. So pick your favorite, okay? So now that's going to be plus 2m e minus v all over h bar squared times psi of x, and that all equals 0, okay? Beautiful. So then now, if we continue along here, we're going to do the same method we did with the ansatz. Cry, pray, guess, solve. We've cried, we've prayed. Now it's time to guess. Okay, so we're going to guess the same guess solution, e to the ax. Okay, and so again, right away, we know that the first derivative of that guess solution is ax, and then we know the second derivative is the a squared ax. Okay, so now I can plug these into my function right here, and let's do that. So second derivative of psi of x is a squared ax, okay, plus, and then now we have all those constants again, 2m e minus v all over h bar squared, and we know psi of x is just ax, and that all equals 0, all right? Now we're going to do the same thing. We can eliminate the eax and the eax, and we get a squared plus 2m e minus v all over h bar squared equals 0. And now let's just keep this going, right? So now I'm going to say that a equals negative, so I'm going to leave this as a squared for the time being. So a squared equals negative 2m e minus v all over h bar squared. And now you might be looking at this and saying, well, this is going to be another situation involving imaginary numbers. That's what at least it looks like for the time being. However, okay, e minus v, we know because v is greater than e, right? Let's write this up here. We know that e minus v is actually a quantity that's less than 0. So we know that that term is already going to be negative, okay? So what I can do, I can factor out a negative and rearrange that so that it's written as negative v minus e, right? So we know that v minus e is actually a positive, okay? But if I make that quantity negative, right? If I say negative v minus e, then we know it'll have the same value as e minus v, right? And so now I'm going to rewrite my a squared as positive 2m times v minus e over h bar squared, okay? And so now we recognize, so I can take the square root of both sides of that thing, right? And that's going to give me a real number, a real solution, okay? So we'll say here now, I'm going to use a slightly different letter. I'm going to say now my solution for A equals kappa, so it's just a change of letter here, okay? So where, in other words, kappa, and so, technically this is, because it can be squared, right? It's plus minus kappa, right? Okay, where kappa is this square root of 2mv minus e over h bar squared, all right? And so what that means, my wave function psi of x is going to equal the following. So I'm going to just pick a new set of letters for my normalization. I'm going to say C, E, and now, so remember, A is really just plus or minus kappa. So I'm going to say kappa x plus dE to the negative kappa x. And this becomes my general solution, my unnormalized solution. And again here, I used a kappa instead of a k because we note here that the k that I came up with right here is the root 2me over h bar squared, all right? I'm going to use this letter kappa to be 2m v minus e over h bar squared, okay? And we can also see this is an equation of either, describing exponential growth in the case of e to the positive kx, and that's exponential decay to the e to the negative kx. And we can see that, right? This is an equation describing exponential decay, which is pretty cool. Now, what about the exponential growth part? Well, as it turns out, if we were to look at psi squared, which is what this kind of picture is showing you right here, right? We can see, right, this region that's showing what looks like exponential decay, and this other region here that looks like exponential growth. All the same, what both of those functions are showing is this dampening of the wave, okay? So it's this exponential solution that's in here that shows a exponentially decreasing amplitude of that transmitted wave. So that's what both of those terms are showing you. And what you also might guess from the region 1 solution, where we got, e to the ikx and e to the negative ikx, right? The e to the ikx, we know, describes a particle moving to the right, so showing the wave front moving this direction. But the e to the negative ikx is really corresponding to a particle moving the other way. So that term we can relate to the reflected wave. Okay, so we can actually ascribe these solutions to their particle counterparts. Okay, and then finally, what we know about